Okay, so in this video I'm going to look at the decay of nuclear material. So before I do, just some key things that you need to know before we go any further. The half-life of any radioactive material is the time taken for the number of undecayed atoms, which we usually give the symbol N, to halve. So it's time taken for the number of undecayed ones to halve. Another key thing, the unit of activity, the becquerel. A becquerel is 1 decay per second. And we also have this equation that the activity is equal to the decay constant times by the number of undecayed atoms. So we can see that both the activity and the decay constant will have this unit of s to the -1. So let's crack straight into it. Okay, so if we have a graph where we plot n, the number of undecayed atoms, against time, it's quite easy from these to measure what the half-life is, because you just look where the original number of undecayed atom is and then go down the y-axis to where it's half, draw a line across, which was this line here. So obviously we started up here, so half of it is here, so you draw a line across, draw a line down, that's your half-life. And if you then work at, well, what does it take to halve again? You are at this point here, draw a line across, draw down, and that will tell you what 2 half-lives are, which is nice and easy. But what you'll notice is that for any radioactive material, the half-life should remain the same. However many of these you do, you'll find it should still be constant. And obviously, further down here, it asymptotes towards 0, although it never actually reaches it, or at least mathematically, and it just basically decays to background radiation eventually. That's sort of the limit of it. Okay, so this graph isn't it's good for getting half-life, but it's not too great for reading anything else from. So what we actually do is we plot a slightly different graph. So if we plot a graph of the natural logarithm of the number of undecayed atoms against time, you get this nice straight line graph here. And actually the gradient of this graph is the -1 times your decay constant, which is quite useful obviously if we want to work out what our activity is or that sort of thing. So this log graph is much more useful in terms of that. So let's move on to look at a couple more equations that you do need to know. Okay, so first these two at the bottom. So we have this relationship to work out the number of undecayed atoms at any given time. We have the number of undecayed atoms we started with, which we call n0, and then we have this exponential of minus the decay constant times time. And this here is basically the equation that describes the first graph that we looked at, which we measured the half-life from. So that's describing that. And this one down here is basically just then saying, well, if that's the case for the number of undecayed atoms, the activity is going to be of this relationship here. It's the same thing. So the activity at a given time is equal to the original activity, or A0, times by the exponential of minus decay constant times time. And from those equations we can get this relationship that the half-life is equal to the natural logarithm of 2 divided by a decay constant. And if you're interested, on the next slide I'll show you where that comes from, but it's not particularly relevant, but it's just out of interest. So why do we even care about these equations and these relationships? Well, I mean, it all comes down to our use of the various radioactive things. And one of those uses is carbon dating, because things like plants actually produce something called carbon-14, so that's the isotope of the carbon that you'll normally come across. So when they die, that carbon-14 then begins its process of decay. So by measuring either the activity or the number of undecayed particles left over at now, we can actually establish when that plant actually lived. And the other useful thing is, if we're talking about medical uses, we're going to want to know when the radioactive sample will be safe. So we want to be able to work out what dose of radiation we're going to give to a person so that we don't exceed the dose that would then become unhealthy. So I think, is it technetium-99, I believe it is. It's used as it's called a medical tracer. So what they do is they actually inject that into a person and then it basically then this, I think it's a gamma radiation source, and that gamma radiation obviously can then penetrate through the body and come out and be detected by our detector. So we can actually map the progress of that isotope through the body. But obviously we don't want a material that lasts a really, really long time. So by using these equations we can work out what the half-life of technetium is, and I think it's something of the order of a few hours, so like 5 or 6 hours I believe. So it's a nice period of time to collect data, but short enough that you're going to actually reduce the overall radiation dose compared to something which has a larger half-life. And I believe the other benefit of it is technetium actually decays into quite stable isotopes, so it doesn't then continue in a chain like some other decays. It actually decays into stable isotopes, which is also pretty handy. Okay, so I said if you were interested that I would show you where the half-life relationship comes from. So obviously the half-life is defined as the time taken for the number of undecayed particles to half. So at the point you reach the half-life, on the left-hand side of this equation, the n would be equal to half of the original n0. And that means that the t at that given time would actually be your half-life time. So I'm just going to scribble that in there. So obviously we can cancel out these n0s here, and we get left with half is equal to e to the minus decay constant, and then you've got your half-life time there. Okay, so obviously now we want to get our time half-life out of that exponential. So obviously we're going to take the natural logarithms of both sides. So if we do that, natural logarithm of half is equal to minus t to the half. Obviously this isn't a particularly nice way to write this, but one of the key relationships you should know is that a half is equal to 2 to the power of minus 1, which is quite neat. So if we substitute that in, and with logarithms, if you have a power inside, you can then move them outside and have them multiplying, which means we have this relationship here. So then obviously we can cancel the minus signs, because obviously in our equation we didn't have any, and that leaves you with, if we rearrange to give you in with the half-life, you've got your log 2 on the top line and your decay constant on the bottom line, and we see we have this relationship here which is exactly equal to the equation that I just stated on the previous page, which you would need to know. And that's how we go about proving that relationship.